Okay, when we start to look at exponential models, we have to remember that all exponential models come in the same form, regardless of the situation, whether it's half-life or population growth or decay or whatever. They are always in the same form. We will start with a starting amount, which we'll call A. We multiply that starting amount by a common ratio, which we'll call B, and we do that X number of times. And that results in an end amount, which we'll call Y. So all exponential models are in this form, and we'll just adjust as we are given the information. So for example, let's say we have a population of Yorktown is 25,000 people, and it is increasing by 3% each year. So the first thing we want to do is write an equation to model the population. Then once we have that model, we want to determine the population after 5 years, and then we'll look at how long it will take us to double the population. Okay, so let's look at our model. So as I said, all exponential models are in the same form. We have a starting amount A multiplied by a common ratio B, and we do that X number of times. So what would the common ratio be? Well, 100% is what we start with if there is no change. So if we have 100% of something, we are starting with the same amount. So we have 100%. Are we increasing or decreasing? Well, we are increasing. It says increasing by 3%. So we're going to add 3% to the 100%. So next year we would be at 103%. If we wrote that as a decimal, it would be 1.03. So I'm going to use P for population. The starting population is 25,000 people. The common ratio is 1.03. And I'm doing that X number of times, and I'm just going to call it T for time in years. So that is my equation that models this population. Now if I want to find the population after 5 years, I'm just going to use this model, and I'm going to put in T as 5 years and determine that population works out to be about 28,982 people. And then in C, it wants us to know how long it will take for the population to double. So now we're looking for time. So here's my model. I'm starting with 25,000 people. It is increasing by 3%. And it takes a certain number of years to do that. And I want the population to double. So my end amount is now 50,000. And we are looking for the value of T. So if you remember, when we're solving exponential equations, we can't multiply the 25,000 by the 1.03. So we're going to isolate for that 1.03 to the power t by getting rid of the 25,000 by dividing, and we'll do the same on the other side, which gives us a value of 2. And that makes sense because we're trying to figure out how long it will take to double. Since we can't change the same base, we are going to use our change of base formula. So it will be log of base 2 divided by log of base 1.05 or 03 will equal the exponent t. We type that into the calculator, and T works out to be approximately 78 years. So it would take about 78 years for that population to double. In this example, we have a purchase of a new car. So the starting value of the car is $37,000. This time it is decreasing or depreciating by 2%. We want to write a model. So the common ratio, B, is going to be the starting percentage would be 100%. That would be no change. Now we are depreciating by 2%. So we're going down by 2%, which means next year it's worth 98%, or as a decimal, 0.98. So my model would be, let's say A is the amount of the car. The starting amount is 37,000. It is depreciating to 98%, and T 4 years. It wants us to know what the car will be worth in 4 years, so we're just going to use the same model but put in 4 for time. And then we can just determine that using our calculator. Works out to be about 34,127.62. And then in C, it wants to know when will a car be worth 12,000. So that's your end amount. So our end amount is 12,000. Our starting amount is 37,000. Common ratio is 0.98, and we are looking for the value of T. So again, we want to isolate, so we'll get rid of the 37,000 by dividing. Do the same on the other side. And that gives us a decimal value. And again, since we can't change the same base, we will use our change of base formula. So we'll do log of the, that's a 3. We'll do log of the end amount divided by log of the common ratio, and that will equal T. Type that into the calculator, and T equals approximately 56 years. So half-life is a specific type of exponential model. It is still the same generic model, y equals ab to the power x. But with half-life, we use specific letters. So we use a initial as the starting amount. So that's our a with subscript 0. That means the initial amount or the start amount. T is time elapsed, and h is half-life. So you'll see the common ratio is a half because it's a half-life. So that is the amount of time it takes for a quantity to decay to half its original amount. And then our number of times is determined by two values, time passed and the half-life it takes to reduce. And that means that, let's say, for example, a sample has a half-life of 2 minutes and 10 minutes go by. That means it's going to reduce 5 times because 10 divided by 2 is 5. So the number of times it reduces in half will be determined by not only the time that has elapsed, but also the half-life that it takes to reduce in half. So for example, we have a half-life of a magical potion is 18 months. If 170 grams of the potion were stored, how much would be left after 7 years? So our starting amount is 170 grams. It is a half-life, so that's our common ratio. Time passed is 7 years. The half-life is 18 months. So you need to have your units of time and half-life in the same units. So if we're going to use 18 months for half-life, we want 7 years to also be in months. So we'll change that to months, which would be 84 months. And so our model is starting amount, which is a to the 0, or the initial amount. Common ratio is a half, and then T over H. So starting amount is 170 grams. It is a half-life. Time passed is 84 months. It takes 18 months for it to reduce in half. If you are typing this into the calculator, you want to put the 84 divided by 18 in brackets because you want the calculator to do that first and then as an exponent. Or you can just divide it and use that decimal. It's up to you. But if we're going to type this into the calculator, you should end up with a result of 6.69 grams remaining. So just make sure if you type it into the calculator, you're doing 170 times 1/2 to the power, and then put that exponent in brackets so that it divides 84 by 18 first, and then it does the exponents. In this example, we have a half-life of a blue radioactive substance. Somewhere deep in a lake is 7 weeks, so the half-life is 7 weeks. How long will it take? So we're looking for time. 900 kilograms of the substance, so that's our initial amount, to reduce to 10 kilograms, so that's our end amount. So again, we're going to use the exponential model of starting amount, common ratio, a certain number of times. The end amount is 10. The start amount is 900. It is a half-life. Time is what we are looking for, and the half-life is 7 weeks. So we will isolate that exponent. So we'll get rid of the 900. I'm just going to reduce that to 1/9 rather than use a decimal. And then I cannot change the same base, so I'm going to use my change of base formula. So I'm going to use log of 1/9 divided by 1, or log of 1/2 equals the exponent, which is t/7. So once I type log 1/9 divided by log 1/2 into my calculator, I get a decimal value of 3.17. And then in order to solve for t, I'm just going to cross multiply. And t will work out to be approximately 22.2 weeks. In this example, we are given a starting amount of 420 ounces. After 79 days, so that's time passed, there is 30 ounces left, so that's end amount. And we're looking for the half-life. So same model, starting amount, half-life, t/h. We are given the end amount of 30, the start amount of 420. We know that 79 days have passed, and this time we are looking for the half-life. So we will isolate for the exponent by dividing by 420. I might just change that to a decimal, so I'm just going to do 30 divided by 420, which is 0.0714. You can leave it as a fraction as well. You could reduce it to 3/42, which reduces to what? 1/14. I'm just going to change it to a decimal. I've got a half. And then we'll take log of the answer divided by log of the base equals the exponent. So I will type that into the calculator. Log 0.0714 divided by log 1/2 is 3.81. That equals 79/h. And then we will cross multiply. Now this time when we cross multiply, we do not get the h by itself. We get 3.1h divided by 79. So we have to do one more step by dividing by 3.81. And then we can find the half-life to be 20.7 days. In the last example, we have a cup of coffee. Starting amount is 140 milligrams. It is reducing by 10%. So this time, it's not a half-life. This time our common ratio will be 100% to start, reduced by 10% is 90%, or 0.90. So we'll still use the same exponential model. We've got 140 to start. We have a common ratio of 90%, and t is time. It wants to know how long it will take for half of the coffee to be eliminated. So our end amount would be 70. We will we will divide both sides by 140 to get rid of that, which leaves us with 0.5 or 1/2, which is what we expected because it says half is left. And then we will solve by change of base formula. 0.5 divided by log 0.9 equals t. And then t is 6.58 hours.